Hello, today I will talk about electrons in an atom. First, I want to refresh your memory by giving you the definition of electrons. Electrons are negatively charged subatomic particles surrounding the nucleus of an atom. So on the right diagram here, I have the structure of the atom. Here's the nucleus. Inside of the nucleus, we have positively charged protons and neutral neutrons. Surrounding the nucleus, we have negatively charged electrons. Before I begin to tell you more about the electrons, I want you to take a moment to think about why neon lights glow in the dark. Can you explain the glow emitted by the light? Take a moment to reflect on this. Well, let me tell you, electrons are responsible for the glow in the neon light. So now I am going to tell you more about the behavior of the electrons in an atom. So I want you to keep these questions in the back of your mind. Where are electrons in an atom? How are electrons distributed in an atom, and how do electrons behave in an atom? So how do I begin? Well, back in the days, scientists discovered that light can emit different energies in the form of wavelengths, leading to a spectrum of different colors. So in the mid-1800s, they found that energy from hydrogen atom can generate a line of different wavelengths, giving rise to colors like purple, blue, blue-green, and red. But the question is, where does the energy come from? Does the energy come from the electrons? Maybe, but let's further see. So according to a physicist, Niels Bohr, he predicted that electrons rotate in circular orbits around the atom's nucleus. And that may help to explain the line spectra of the hydrogen atom. So Bohr postulated three key points. So the first point is orbits of certain radii correspond to certain energies for the electron. Second, the electron, once in an orbit, is present in an allowed energy state, which does not emit energy and spiral into the nucleus, but instead the electron emits or absorbs energy only as the electron moves from one energy state to another. In other words, as the electron transitions from one energy orbit to another energy orbit. In doing so, he demonstrated the energy states of the electron of the hydrogen atom for several orbits. So here on the right, I'm showing you a diagram of the energy states of the hydrogen atom. So on the y-axis, I have energy in terms of joules per atom, whereas the black lines here denote individual orbits in the form of n, called the quantum number. So n equals 1 is the ground state or lowest electron orbit, whereas values greater than 1, such as 2, 3, 4, leading to infinity, are excited states of the electron or larger orbits as the number increases. So Bohr predicted that when an electron moves from one orbit to another orbit, energy is either absorbed or released. So let's refer to the scenario where energy is released. When energy is released, electrons move from a higher orbit to a lower orbit. So assuming that we are in orbit 2, so assuming that the electron is in orbit 2, the energy, the electron transitions into orbit 1 or ground state while releasing energy during the transition. So note that the electrons do not emit energy while in the allowed energy state. So that's how energy is being released and energy is thus lowered, making the atom stable enough. Another scenario is when energy is observed. When energy is observed, electrons move from a lower to a higher orbit. So we assume that the electron is in orbit 1. The electron moves up to orbit 2, absorbing energy in the process, causing the electron to be in an excited state with more energy, resulting in a less stable atom. To make this simpler, let's reflect these energy states in the structure of the atom. So here we have the nucleus. Surrounding the nucleus are orbits of distinct radii corresponding to specific energies. So here we have orbit 1, orbit 2, orbit 3. Supposing that the electron is in orbit 2, it moves to orbit 1, releasing energy. So supposing that this same electron moves to orbit 3, it absorbs energy. And to further put this into perspective, imagine that you're climbing a ladder. Your foot is the electron. As you climb the ladder, one step down, your energy goes down. But as you climb the ladder, one step up, your energy goes up. But unlike Bohr, who taught that electrons orbit around the nucleus, another physicist, de Broglie, suggested that electrons go around the nucleus of an atom like waves and therefore has wavelength to represent the line spectra of the hydrogen. Indeed, de Broglie's theory was proven to show that electrons act as wave. So here I'm showing you a diagram of the structure of an atom again, and here the electrons are behaving as waves around the nucleus of the atom, generating wavelengths as shown here in this wave diagram here. So from one crest to another crest, that's what we call the wavelength. Okay, so this concept was shown or proven when electrons were shown to pass through a crystal, thereby exhibiting wave-like properties. So right now below, I'm showing you an image of a transmission electron micrograph illustrating atoms on top of columns in the form of white dots. So here's the picture, and these small white dots are actually atoms. Today, electron microscopes are developed to examine these wave-like properties of electrons at the atomic level. Isn't that cool? It's very cool, I think. However, as true as de Broglie's theory is, another physicist, Werner Heisenberg, stated that there is no limit to knowing precisely the position and energy or momentum within an atom in space at the same time. Remember, no limit. Like for example, a football. If the location of a football on a field is accurately known, then less is known about the energy or momentum of that football if the direction of this football is changed. So thus coming back to the electron, There is really no idea in knowing exactly where the electron resides in an atom within space. But the probability of finding an electron in an atom at a particular position in space can be identified. How? It turns out that a wave equation is possible to determine the behavior of the electron. Physicist Erwin Schrodinger proposed the wave equation. So this equation was initially developed to describe motion waves and matter waves. So let's take, for example, the guitar. You pull a string on the guitar. The string generates a series of high frequencies and overtones. Likewise, the electron exhibits similar properties of these waves with lowest standing and highest standing energy. Furthermore, just as harmonics of guitar contains notes and amplitudes, so does the electron. Isn't that amazing, right? Waves do not travel in space, yet these electrons exhibit the features of waves. So back to the wave equation. Schrodinger solved this wave equation into the wave function demonstrated here as phi. So phi denotes the probability that an electron will be detected at a particular location within an atom. How is that probability being represented? So I forgot to say something. So instead of phi, the square of the phi denotes the probability that you can detect an electron at a particular location in an atom within space. So how do we represent the probability of this electron? It is represented in the form of an electron density distribution. So here in space, we have the z, y, and x axes. Think of the origin as the nucleus of the atom. The probability of finding an electron will be higher if closer to the nucleus of an atom compared to farther away from the nucleus of the atom. So to summarize, electrons behave like waves around the nucleus of an atom. Since there is no exact region in which an electron orbits, scientists like to think of the region as an electron clouds. With that said, I would like to end with the last description of an atom. An atom consists of a nucleus surrounded by an electron cloud. And this is the last of my video here, but I would like you to take the moment to reflect now on why neon lights glow in the dark. Think about electrons, think about energy, think about waves to answer this question. So with that, I leave you with one question. Do neon lights absorb or release energy to glow in a dark room? Thank you for listening to my video.